The title of this session is Partnering for Market Uptake. My name is Dr. Henschel Strauss. I am the Center Manager of the Photonics Center in the manufacturing cluster of the CSIR. And both these presentations is going to involve laser and photonics technologies and how we partner with industry to make them more competitive and to keep jobs in South Africa and to build our economy. So the recipe for this is quite simple. We develop technologies to make industries more competitive, and then we use that technologies eventually to spin out new entities and new companies. In the first talk that you'll see here, that's very in the, it's still in the, it's just been conceived, and the second one, the baby is ready to be born. But the ultimate goal here is to develop, to create new jobs. We cannot just develop technologies, pat ourselves on the back, and then move on to the next thing. Then the baby dies in the womb. The ultimate goal is to take this and to create entities and to create jobs and to keep jobs in the country. So the first talk is about a novel laser system development with a commercial partner, and that commercial partner is the De Beers Ignite. And we've got two speakers today. The first is Mr. Gordon Taylor. Gordon is the head of commercial technologies of the De Beers Ignite. He has spent the last 33 years in the R&D and deployment and support of innovative technologies for the unique requirements of the De Beers Group mining and exploration operations. He's immigrated here from the UK in 1990, just after he's done his MPhil in laser physics, and ever since he's been in De Beers, first as a junior research scientist, and then he's progressed over multiple project management and research and development departments, and eventually now he's with the South African De Beers technology functions. So that's Gordon, and we're very happy to have him here to come speak with us. And the second speaker we've got is Dr. Darryl Naidoo. Now, Dr. Naidoo is a principal researcher, and he's currently the research group leader of the Novel Lasers Group at the CSIR Photonics Center. He joined the CSIR as an MSc student in 2009, roughly the same time I joined, and he went to complete his PhD in physics in 2015. His research focus is primarily on laser beam shaping. He has over 40 peer-reviewed journals to his name, with highlights such as Nature Photonics, Optica, Nature's Light. He's honorary research fellow at Wits University. He has multiple awards, and he's also received the silver medal from the South African Institute of Physics for all of the research that he's done. So that's Dr. Darryl Naidoo. So both he and Gordon will speak about the laser that they've developed for the De Beers Ignite. So I would like to welcome you onto the stage.
First of all, I'd like to say thanks everybody for not disappearing off to get coffee and snacks, and for persevering with us today. It's a great pleasure for me to be here addressing you today with my co-presenter, Dr. Darryl Naidoo, on a very successful laser technology development collaboration between the CSIR National Laser Center and De Beers, the world's leading diamond company. The down one. Oh, so that's that one. Okay. In 2021, the global diamond production was approximately about 128 million carats. Of that, De Beers production was roughly 33 million carats, or approximately 26%. The De Beers Group production is the largest single production by an entity, followed closely by the Russian company Alrosa with 32 million carats. with the balance of the majority of the rest of the diamond production coming from junior miners or the informal or artisanal sector. The De Beers Group consists of three main mining entities. There is the managed operations entity, which runs the Venetia mine in the Limpopo province of South Africa, and the Gachokwe mine in the Northwest Territories of Canada. And then we have the two joint ventures. The first, Namdeb Holdings, is the collaboration with the government of Namibia, comprising of the Namdeb land mining operations along the west coast of Namibia, and the De Beers Marine Namibia, which operates a fleet of purpose-designed marine mining vessels that extract diamonds from the seafloor of the same Namibian coast. The second, and probably the most important joint venture, is the Debswana joint venture, the 50-50 partnership with the government of Botswana. Debswana operates two of the largest diamond mines in the world, Jwaneng and Arapa mines. The important context for the technology development with the CSIR is that Debswana accounts for roughly 80% of De Beers production, or 20% of global production worldwide. The processing and the recovery of diamonds starts with the mining of the diamond-bearing ore. This can either be original host kimberlite pipes, such as those at Arapa, Jwaneng, or Venetia mines, or those diamonds that have been eroded from the original kimberlite pipes and then transported by ancient river systems to the beaches and seafloors of Namibia. Once this ore has been mined, it is then crushed to liberate the diamonds, and then a density separation process then follows, which removes the majority of the non-diamond bearing material. What is left is then put through an electronic sensor-based particle sorting process before the pure diamond concentrate is then dispatched from the mine. The technology used in the electronic particle sorting process is proprietary to De Beers and has been researched, developed, manufactured, and supported by De Beers Group Ignite, one of the technology development functions of the De Beers Group. The final stage in this particle sorting process is termed single particle sorting. At the Jwaneng mine in Botswana, there are 4 final stage single particle sorting machines, and these are employed to produce a final diamond concentrate, treating both material from Jwaneng mine and material transported from Arapa mine. And critically, hence, all diamond production for Debswana is sorted through these 4 single particle sorters. And remember, that's 20% of world diamond production. The technology employed is based on the laser Raman technique, which produces a unique color change in the laser radiation when it interacts with the diamond. These sorters were originally developed by De Beers in 1995 and have been deployed since 1999. Since then, De Beers Group Ignite has upgraded, overhauled, and redesigned to keep these systems up to date and operating efficiently. One of the key components is the laser system. It utilizes a neodymium YAG infrared laser with a relatively high power of 35 watts to produce a measurable Raman signal with low fluorescence background, both of which are critical for good diamond identification. However, it became increasingly difficult to find a sustainable and sufficient quality laser system to keep these sorters operational from the traditional OEM laser manufacturers in North America, Europe, or Japan. Hence, this is when we approached the CSIR National Laser Centre through our long-standing contacts to understand if they could assist with the development of a suitable laser system.
Thanks, Gordon. Hi, everybody. Good afternoon. So many of you might be wondering, what exactly is a laser? You've all seen laser pointers like this one here, or you've heard of laser cutting systems or laser welding systems. But what exactly is a laser system in itself? Well, it consists of 3 main components. The first component is this little pink component here. That's called the active medium. It could be a solid crystal, it could be a gas, it could be a liquid, but it's highly specialized in that it contains specific molecules that will absorb the input energy that will come through here. So this input energy is also a variety of different sources. It comes from other lasers, it'll be a source of electricity, and just a variety. Now what happens in the process is that when I apply this energy into my gain medium, I get little particles of light that get emitted. Now these are called photons. So the photons then bounce back and forth between two mirrors in a cavity-like structure. And if I make one of these mirrors partially reflective, then some of the light will propagate out. And that's where you get your laser. Very simple, very basic process. Not so easy to make, though. But when we looked at the project with De Beers, there were a couple of requirements. The first, obviously, was a specific wavelength requirement, right? It's a certain type of energy requirement. And that's where we now get to choose what type of gain medium we want. So when Gordon mentions a neodymium laser, the actual crystal itself has got neodymium ions in it. The second part is it needs to be stable, robust, and vibration isolated. You can imagine in a mine where there's huge machines, and this particle machine is probably three stories high, there's a lot of vibrations. That's going to cause a lot of issues on a very sensitive piece of equipment. It also needs to have a very narrow line width and be highly efficient. Now, these are really important properties and processes that are going to allow this actual diamond sorting process to happen. So the first part we had to look at is the actual design considerations. Now, there are two types of laser systems that exist in this neodymium regime. The first one is when the input energy comes in from the side onto our laser crystal, and then we get a little laser output here. This is really good for energy extraction. It's compact. It's very easy to assemble. The problem is that the beam is not very great coming out, which means it really just will propagate from one place to another in a not so controlled manner. There's very limited customization, and the stability of the system is highly reduced. So when there's lots of vibrations in this actual system, it's going to cause a lot of problems. This is currently a lot of the technologies that are used that De Beers have used in the past. So we decided, well, let's go to the other system, what we call an end pump laser. So we have our input light source that comes in from one direction into the crystal. And what this does is it doesn't give us as high energy extraction. It's not as compact. It's a lot more difficult to assemble, but the beam is much better. It's highly customizable, and there's very high stability. So given the power requirements and the requirements in general by De Beers, we found that we don't need a lot of energy from our system, and we don't have to make it as compact as compared to what current competitors have, which means we've got a little bit of play to work with. So that takes us then, since we're the CSIR, it takes us into the lab. First to a drawing board, and then into a lab. After lots of conversations with the team, we finally decided on a design. And this is what a typical laser will look like in a lab. These are all the different components. There's a crystal that's positioned inside here. These are the different energy sources that then get directed into the crystal using a series of lenses. These are the mirrors that basically form the actual laser cavity. And here, we just measure the power output. But we found that the system was a bit bulky and was a bit sensitive. So we made everything a lot more compact. And when we think about compact, the size of that system is probably about that big, maybe about 45 centimeters wide. It's actually quite small. So since that works, we then go straight into our actual design. Now the design is quite a critical part here, because none of the components that we actually use in our lab demonstrator are necessarily going to be used in the actual final product. This means we've got to look at a variety of mounts, a variety of cooling structures, a variety of crystals, as well as a lot of the other requirements that De Beers had personally asked for in the laser system. This is what makes the system so great. When working with somebody like De Beers or working with a client, you get to customize your system exactly to what they would like it to be. So based on the design, we get a lot of these components bought from overseas, which is a problem, because in South Africa, we don't have any local content in terms of having these readily available. So we buy a lot of our stuff from overseas, from Europe and the States. But there are a lot of components, like our little crystal holders, that we can get manufactured and designed here. Once we put everything together, do a little bit of alignment, we switch on, and as you can see, a nice little laser light coming through there. Now, these lasers are actually invisible to the naked eye. But for some reason, our camera phones can actually see the light, which is quite cool. And it shows it as being this pinky purple color. Now, having this laser box as it is here, or having this laser system sitting as it is here, is not exactly the final product. What De Beers want to now do is be able to get this laser system into their actual final particle sorter. So this means having to put the laser light through an optical fiber. Now, a lot of people would have heard about an optical fiber, and you would have heard about optical fiber communications. But how we work with the internet today is all run using fibers. Fibers are just basically a nice long piece of glass that you can then propagate your light into to transport it from one place to another. Now, what this means is that I can then bend my fiber in a variety of directions and position it so that the light will then come out in those different directions. So we had to have a little fancy fiber design to be able to couple it very efficiently. Now, typically with current commercial lasers, especially of this what we call a solid state variant, the coupling efficiency is around about 80%. But that caused a lot of problems in their systems in the past, which caused these fibers to consistently break. So we had designed it in such a way that we achieved about a 96% coupling efficiency. Basically no loss. That's the theoretical limit of what you can achieve. So in doing so, we have put our system together and then we couple our light. Now, Gordon had mentioned that they were looking at roughly 35 watts. Our system was performing at about 37 watts with only about 50% of its full capacity, which is fantastic, which means that over time, naturally, the input light energy tends to degrade and the systems start to degrade. But that means if we're only running at 50% operational capacity, we can keep running the system for many, many years to come. Now, this is still what we like to call the brass board. We have it all fitted together. Now we need to start packaging everything together. So what that means is that we basically have to build a box around it. By building a box around it, we do so, put everything together, and then we've got to add a ton of sensors. We want to measure everything. The power, we want to be able to measure the temperature, the stability, and everything, along with the other sensors that De Beers would also like to monitor in the system. So all of that fits inside here. But that's not where it ends. If we have a look at some of these really pretty pictures, you can see some of the components inside the laser system. We just thought we'd put this down because it's quite nice for marketing. The final part is that the laser box is just one component, where the actual laser sits is one component. The rest of it now comes into play. It's having to have a power supply, having to put a chiller, having complete water flow to actually water cool our systems. There's so much heat generated in these crystals that we have to run water over them to be able to cool them as effectively as possible. And then we've got the very daunting task of having to look at the full electronic control. Now, typically with lasers that you buy commercially, you will get your laser and you'll only be able to control exactly what the laser does, and that's about it. Any other subsystem that you want to now integrate your laser with, you have to do that completely separately on your own. But with De Beers, we had worked directly with them to be able to put a complete laser system into place, not just a laser. So what this means is that this laser will now completely integrate into their system just by plugging in a couple of cables. They don't have to do anything extra on top of that. So as you can see, a lot of work goes into the electronics to be able to do that. But if you put some covers on it, it ends up looking very nice and very neat and allows you to have complete control of your entire system. The final part is just the tinker and the assembly, just basically putting everything together. So here we've got our rack where everything sits into place. Here we've got Justin that's busy working on the plumbing, and the laser now starts to take shape. During the course of September this year, we had a demonstration of this final laser product with the team from De Beers. Now, we were really happy, really, really happy. This is the team's first commercial product that we've developed since the team started. How long ago was that? Maybe eight years ago. Team's first commercially viable product that actually goes out. This is the team. We've got a mix of everybody from CSIR and De Beers that had worked on the actual product together. But that's not obviously where it ended. We now had to get this laser from CSIR to De Beers. So your heart skips a beat now. Is it going to make the trip to Johannesburg? And is it going to work when it gets there? Thankfully, it did. It performed exactly as it should have, and now I believe that the laser is sitting in a mine in Botswana. So I'll hand over to Gordon.
Great, thanks, Darryl. Yeah, if Darryl's heart skipped a beat in trying to get the laser from Pretoria to Johannesburg, mine must have skipped several beats in trying to get it from Johannesburg to Jwaneng in Botswana. I think what we've learned about product development and what in collaboration with the CSIR is exactly what Darryl talked about earlier on. The peripheral components, the chillers, the power supplies, the control systems are as important as the fundamental technology. And then when it comes to producing a product, then the commercialization stage is more about how people will use the technology, how they will interact with it, how they will maintain it on a day-to-day basis, how they need to be trained on it. And again, rather than, and this commercialization stage is more about ensuring people can work with it rather than the actual technology itself.
Yeah, I think from a CSIR side, we clearly learned that doing technology development toward product development is a multi-skill process. It's not just about getting the scientists and the engineers together in a room. It's actually about having adequate project management, understanding completely your supply chain. Now, the supply chain goes across a skill level. It also looks at variety of procurement. Now, we know that procurement in the country within government organizations is a little bit of an issue. But with adequate planning and the correct positioning of this, then we are able to actually get through the whole system. What's remarkable about our understanding so far with working with development is that actually all the necessary skills are available in the country. It's not like we have to go and look elsewhere in the world to identify all the necessary skills. A lot of the skills already exist here. We're just not necessarily aware of them in terms of developing new products. And the final part about this is it's often in the details. I think the largest part that we spent on the project was deciding on a name. That was the part that took us the longest. Just deciding on the name. It went back and forth, and it was a whole different set of languages and everything. And finally, we landed up with the name Gem Layers, because it just makes sense. Our laser is going to be working with gems. But it's in those finer details, really looking at each component and analyzing everything so that it works in a completely wonderful manner.
Okay, so where to from here? So as I mentioned earlier on, we did transport the laser system from our operations in Johannesburg to the Debswana Jwaneng mine. It's currently been successfully installed. The commissioning of the new laser system went extremely well, very smoothly. Probably one of the best installations of a major system that we've done for some time. To date, when I did this slide, it's been operational for 2 weeks. It's now been 3 weeks. And so far, the results coming back is that the power is stable, which is exactly what we wanted. And we have got a very good initial good results from the sorting system itself. One of the really important operating parameters for this final stage single particle sorting is something we call diamond by weight. It's essentially a measure of the purity of the diamond, the material that gets exported. Previously, Debswana were operating with a purity of 98% diamond plus or minus 1%. And so far, the initial results that we've had using Darryl's and the CSIR's laser is we are getting diamond by weights and 98.9%, 99.1%. So these are some of the best results that we've ever had. We'll continue the trial period up until January in agreement with our Debswana partners as well. And then should that trial period be successful, which judging by the initial results I'm very confident about, then there will be an additional 3 units required from the CSIR as well.
So from the CSIR side, we want to basically update our laser system and our laser design. Having one design to work with is fantastic, but just keeping that updated and keeping it to modern tech is important. We also want to do something that's probably most important, is making it very cost compatible. So the issue is that we're able to make it with the same cost as what international competitors can do, but we know definitely based on the development so far that we can make it far cheaper moving forward and more efficient. That will take time, obviously, and investment to go into that, but it's really an important part for us to do. We also want to harness this platform for future developments. So future developments with De Beers and future developments with other companies. Having now this capability in the country to be able to create such lasers and do them really well, we can now use this actual platform to move forward and then work really as a collective for further technology development. So working more with De Beers moving forward to get a lot more technologies out and tested.
I think what has been really gratifying through this whole project is that yet again it has reaffirmed with definitely myself and my experience in this country over the last 33 years is the technological capability of South African institutions is world class. What it also has, as Darryl said earlier on, is provided us with a template for future industry collaborations and hopefully, and Darryl will explain a little bit, to generate other markets for this for the gem laser system.
So in terms of a context and really in the theme of this conference, this really provides South Africa and the CSIR with manufacturing capabilities in lasers and laser systems. But it goes a little bit beyond that because the future prospects of developing this technology even further will basically require us to have more skilled manpower. So that's a very large impact, especially with the idea of creating jobs and creating more skilled workforce within the country. We then basically, this unlocks the need to have dedicated training in systems development and laser development as well. And last, I really like this saying normally, and I think most South Africans can agree, local is lekker. And really, localizing technologies for impact is what we've been trying to do for the longest period of time. And it just goes to show that the quality that we can produce here is as good as or even better than what exists internationally. And we should never just overlook that process in terms of the development.
Okay, just to end off there, the experience that we had has definitely encouraged us to do much more, especially from a De Beers perspective. So we'd like to expand on the collaboration with other technical challenges for De Beers Group Ignite. We use X-rays for identifying diamonds as well, so there are opportunities to investigate high voltage power supplies for X-ray generation, potentially using other fiber laser types that would replace some of our older helium neon type laser systems, and then even perhaps beyond sort of radiation generation to radiation detection and helping and assisting us with X-ray detection systems as well.
And in terms of the CSIR and exploring other technologies in the gems and in the mining industry in general, we have capability within the novel lasers groups, within the novel lasers group that obviously looks at lasers, but along with scanning systems, along with measurement systems. So the measurement systems are a variety, but I mean typically on power or even on the actual process itself. Optical coherence tomography, if you pop into the exhibition hall, you will see that there's a dedicated system there with Photonics written all over it, which is a really fantastic compact system that has been developed. And then since we also develop fiber lasers in the group, we will then be looking at working again with other wavelengths, like Gordon has suggested, with basically replacing some of their current older tech. So these fiber lasers will also unlock a lot of new opportunities. And with that, I'd like to say thank you very much.
Okay, thank you very much to Darryl and to Gordon. We've got time for one question from the audience. Yes.
Hi there. Great presentation. I just wanted to find out a bit more, if you could chat briefly, about when you mentioned that typically laser systems laser is quite stock standard, and then a subsystem would have to be developed on top of that and separately. Whereas with you, with De Beers, you guys kind of did that simultaneously in tandem. What was that process like briefly? And do you feel like what you did was novel work, or are competitors around the world doing something like that? Yeah.
Yeah, so I'd probably say it's not completely novel, but it's a complete system development. So for instance, if you've got two separate machines, you have to then interface them to be able to speak to each other, like at any given point. And typically that means you would then have to create a new subsystem to connect the one part to, and then connect the other part to, and then have a control system there. What this does now is that the control system is directly attached to the laser system. So basically the new system can just be plugged in, and they can already talk to each other immediately. So it makes that development much faster in terms of integrating it into larger processes.
Great, thank you very much. Sorry, I'll give more time at the end for questions, but we need to move on to our next speaker. Oh, yeah, sorry, before we go. Sorry, Gordon. Just want to hand you something small, an appreciation, thank you.
Thank you very much. I really appreciate that.